Now we will look at ensemble methods as a way of regularizing in machine learning. So the idea here is that we train and average an ensemble, so multiple machine learning models, in order to avoid the susceptibility of individual models to have test set errors. So basically we want to reduce the variance of our estimator by averaging over different models that have been trained on different subsets of the data or different samples of the data or different model architectures, or perhaps other realizations of stochasticity. When we use stochastic gradient descent as an optimizer, we have stochasticity in the parameter, so we may just rerun the model multiple times, rerun the training multiple times, and then average over. Yeah, so the idea here is reduce the test set error by reducing variance via averaging of different sources of stochasticity. And one technique to do this is bagging or bootstrap aggregating. And the idea here is to subsample the training data, so to construct k different data sets by sampling from the original data set with replacement. So that's like bootstrapping. And then we train k different models on each of these samples and average them. And if we do this, for example, for regression, then we can actually get an expression for how this bagging procedure affects our test set error. So let's say the test set error of an individual model is Gaussian distributed with variances V and covariances C. Yeah, that's just a very simple error model for now. And these are the variances of the individual test items and covariances between them. And in this case, for the simple parameterization of the error, we can show that the expected test set error after the bagging, so of the ensemble model, has this form here. And we can analyze this form for two interesting cases. So the worst case is that all the errors are perfectly correlated. So the covariance matrix is shows that the covariances are equal to the variances. And in this case, the C here becomes V, and this expression simply evaluates to V. So it's K divided by K times V, so we have V. So that means we haven't gained anything. Our variance is still the same as before. So we've just done more work without improving the result. The best case, however, is that errors between test items are perfectly uncorrelated. So our covariance matrix is diagonal. And then this expression reduces to V divided by K because the second term disappears. So that means our variance and thereby the test set error reduces if we increase the size of the ensemble that we average over. So the ensemble is always at least as good as any of its members, at least in the expectation, but often significantly better. And the disadvantage, of course, is that we have to train multiple models, and this is more expensive. So we spend k times as much work as before. Now let's look at a bagging method for neural networks, and that's the dropout method. That's an important algorithm that is still being used a lot, and this was used, for example, in the 2014 AlexNet, which was a landmark result in deep learning because it substantially increased the performance on the ImageNet challenge with respect to previous shallow learning algorithms. And dropout was an important component in the performance of this network. So how does dropout work? The idea here is that we want to do model averaging or ensembling between different neural networks with different architectures. And we consider here a base network that is in this example fully connected. So these are dense neural network layers, and we just have a very simple neural network with 5 neurons here. But the principle also holds if you have a much more complicated network, or also if you have a convolutional neural network. And the idea here is that we want to consider different subnetworks of this fully connected network. And we consider a valid subnetwork whenever we have a connection from inputs to output, at least one input to the output. So here are all the subnetworks of this simple 5-neuron neural network. And some of these are valid neural networks because they are sufficiently connected, and some are not, like this one or this one. We can argue whether dropping some of the inputs is a valid operation or not. That depends on the learning problem. So when you have a lot of redundancy between different input variables, such as in image classification, where the individual inputs are quite redundant and you can certainly give up some of them without destroying the learning problem, then this is fine. But in other learning problems, this might not be fine. So anyway, we formally define such an ensemble of subnetworks. And now the idea is we want to average overall valid subnetworks over the predictions of all valid subnetworks. Obviously, we cannot do this by just enumerating all subnetworks, training them separately, and then averaging, because this would be computationally completely intractable. So Dropout is doing this online during the training procedure of a single neural network. And the idea is the following. We define a mask vector. And this mask vector contains an entry for every neuron, for every input and hidden neuron. And it defines which of these neurons are active. So we take our original neural network graph and we expand it by adding these mask variables. And what we're doing here is we simply take every neuron, multiply it with a corresponding mask variable, and then we obtain a masked neuron. So if this mask is 0, has a value of 0, this neuron is switched off. If it's 1, it's just kept. So the mask network, the mask vector defines the subnetwork that we are considering at the moment by means of the values it has. And now when we train, then for each mini batch of data, we sample the mask vector. We define a probability, p keep, for every neuron to keep it active, so to sample the 1 value here. And then this just defines a computational graph that we can evaluate forward and backward, and we can use it in the backpropagation path. Okay, typically we keep input neurons with a higher probability than output neurons because they're usually considered to be more essential for the learning problem. But these are hyperparameters and they can be set in the usual way by minimizing the validation set error. So Dropout has the advantage that it's cheap. So it's we don't have to explicitly train independent neural networks that have been generated by subsampling the initial network. So we do this online during the training procedure of one neural network, and evaluating this extended computational graph, which has these mask variables in it, is not much more expensive than the original graph. And this is also a quite general method, so it works with almost any neural network architecture, and it works well with stochastic gradient descent. So for these reasons, Dropout is used a lot. Another topic we have to speak about are adversarial attacks or adversarial training. So it's certainly true that neural networks have reached very impressive performances in various tasks, but the question is how much understanding is behind it, or how much robustness also. So what type of errors can a neural network make that we consider to be trivial or unnecessary errors? And that leads us to the question of adversarial attacks. So an adversarial attack is, if we talk about intended perturbations, the following. So we take a neural network and we ask the question, if we make small changes, small perturbations to the inputs, with what type of perturbation can we enforce the largest error in the neural network? So basically we are testing where is the neural network the weakest to attack, to make it make wrong predictions. And this could be, so this vector on which we perturb the inputs could be defined on the whole input, or it could be defined, for example, on single pixels. So one question could be, if we take an input and we are only allowed to change a single pixel, can we do that and get a wrong prediction from the neural network that has done a correct prediction before? That should obviously not be the case. Images are clearly very redundant, so if we just knock out a single pixel, you shouldn't change the answer, but often you can change single pixels and change the answer. Another aspect is random perturbations. So you take an input image and you add a small multiple of a random noise matrix, let's say Gaussian random variables. And then you can find that some neural networks can be easily perturbed by this. So in this example, here we predicted that this is a panda with some confidence, not a very high confidence, but some confidence. And then a small addition of noise turns this into some completely different prediction. And this difference is not even perceivable for humans. So we don't see this as humans, that these images are actually different. And because these kinds of perturbations are sort of a weak point of neural network, we make some changes in this high-dimensional feature space on which we operate. And because we have this highly nonlinear function that we learn to map inputs to outputs, we somehow found a weak spot of the separation plane, or the separation manifold between the classes that we are attacking here. And this leads to an error which seems completely unnecessary to us as humans, and this is something we would like to avoid. So this is a weak spot of neural networks, and therefore it may be a good idea to try to reduce the susceptibility to these sort of errors during training. So we can do adversarial training, where we train, for example, a classifier, and we include these adversarial attacks during the training in order to make the neural network more robust against them.